All right, so we have a problem here. We have a bullet. It tells us it is 10 grams. It's initially moving at 1,000 meters per second. It strikes and passes through this 2 kilogram block initially at rest. So the bullet comes through traveling 400 meters per second. And we are asked about the maximum height the block will rise to. So there's totally a collision here. The collision, for the collision itself, momentum needs to be conserved. That's true in any collision. Now, in terms of the type of collision, if you remember, the types of collisions are elastic and inelastic. There is the subset that is perfectly or totally inelastic, meaning the objects stick together, which is not the case, because this problem tells us the bullet emerges from the block, so it continues on. The difference between our types of collisions is not whether or not momentum is conserved. Momentum initial of a system has to equal the final momentum of a system for any collision at all. The types of collision tells us whether or not we can say the kinetic energy the system has initially is there or not. So elastic collisions are defined as collisions in which the kinetic energy of the system as a whole is still kinetic energy. Inelastic, the kinetic energy of the system is finally not the same. Some energy, some of that kinetic energy is transformed into other types. And so here, if we know absolutely for sure we have an elastic collision, we could solve this entire problem using conservation of energy. But we have to be absolutely 100% sure that's the case. And it turns out it is not the case. This problem is not elastic. The way I know this, I imagine, okay, if I could go pick up that block after this has all occurred, if I looked down on the block, I would see a little hole. The bullet, in order to pass through the block, will have bored a little hole through it. The block looks different now. It did not have a hole to begin with, it does now. That is why I know this is inelastic. Some of the kinetic energy had to turn into some thermal energy, and whatever energy was required to make that little hole in the block. So I cannot use conservation of energy alone to solve this problem. I must use momentum for the collision itself, and then I can use energy to look at what the block is doing after the collision. So if I go ahead and say the bullet is object 1, the block is object 2, I'm going to say that M1 V1 initial plus M2 V2 initial is going to equal M1 V1 final plus M2 V2 final. I know the block is not moving initially, but the bullet is. The mass of the bullet is 10 grams, which we want in kilograms. The initial speed of the bullet is 1,000. It's completely pointed upwards. So I'm essentially finding this conservation of momentum in the y direction specifically. Finally, the bullet is now traveling 400 meters per second. If it has slowed down, that means the block had to gain that energy, or sorry, that momentum. So the momentum of the bullet finally, plus the momentum of the block finally, those have to add up to the momentum of the bullet initially, because it was the only one moving initially. This allows us to find how fast the block is traveling immediately after the collision has occurred. So let's put those values in. 2, I'm getting 3 meters per second. All right. After the collision. Now this one, we need to slow down and think this through for just a second. The collision itself, the time frame is incredibly small, right? If we were watching this, we really wouldn't hardly see much happen, because this bullet, 1,000 meters per second, that's over 2,000 miles per hour. 400 meters per second, that is what, 800-900 miles per hour. So that bullet is in and out before we can even blink. When we say that the block is traveling at 3 meters per second immediately after the collision, that means we see this block right here starting to lift off the supports it was on at 3 meters per second. The bullet is long gone. And so now, for the block itself, the bullet got it to move, which means the block has kinetic energy, and the block's kinetic energy will turn into the block's potential energy, that interaction with the earth due to gravity. So we can use conservation of energy for the block itself. The bullet is long gone. There's no interaction anymore. So we can say that this 1/2 mv squared of the block is going to turn into mgy, so it's going to rise up to a maximum height. Y final being a maximum height means a V final up here of 0. Right? Just like tossing a ball in the air. It slows down, slows down, slows down, gets to a maximum height that instant. Its velocity 0, and it starts falling back down. And so we are just saying its kinetic energy is turning into potential energy. And we can find, see, mass will cancel. We can find that maximum height knowing how fast the block is traveling immediately after the collision. How fast does it get going because of that bullet? All right, so 3 squared divided by 2g. Getting 0.46 meters. So just under 1/2 meter is how high that block will go. So energy and momentum can be used in similar problems. Just be careful in terms of when you're using both equations. Technically, energy is conserved, but if we were, for the whole thing, but there is definitely thermal energy generated. And we don't have enough information to calculate that to begin with. Once we've solved for that final velocity through the conservation of momentum, we could figure it out. We could figure out the change in kinetic energy, essentially. The collision itself happens so fast that the block will not have raised any height during the collision. There's no external forces. It's just the forces between the bullet and the block. So we could calculate the thermal energy generated by taking the change in kinetic energy of the system. But we had to have calculated this final velocity of the block through conservation of momentum first.